All right, we are back. We are looking at review 4, page 1. So let's grab up that review. Take a look at page 1. Suppose you are testing the claim that the mean weight of a tennis ball is 12.5 grams. If you commit a type 1 error, you would, so what would we do there? Well, that type 1 is when you reject the null, but you should not. So we reject the null hypothesis when we should not have. We should have failed to reject. And so in the context of this problem, that would be, we would conclude the mean is not 12.5. We conclude the mean is not 12.5 when really it is. Okay. The second part, if you commit a type 2 error, what would we do what? That is, that's actually just I guess. That's when you fail to reject. You fail to reject the null. When you really should have. And so in the context of this problem, you conclude the population mean is 12.5. When it really is not. All right. For a chi-square test, for standard deviation, how do you find the degrees of freedom? Chi-square is just n minus 1. Suppose you're testing the claim the mean weight of a tennis ball is 12.5, 5%. What is the probability of a type 1 error? Probability of a type 1 error is always alpha. So if alpha is 5%, then the probability of a type 1 error is also 5%. How do you reduce a type 1 error? You lower your significance level. Just lower the significance level, or alpha. All right. In a linear regression problem with n equal to 18 data points, so that's like an xy points, we cannot use the regression equation to predict a y value for a given x value at the 5% significance level unless r, and they actually have it as the absolute value of r, we're just going to call it r, is greater than what? Use from the chart. So here, I brought the chart down. I posted this. This is on Blackboard under sheets you get to use for a test. But if you take a look at this, there's one difference here. For this one, the degrees of freedom is n minus 2 because there's an x and a y. So since there's two variables, you actually do n minus 2. So for that particular problem, they said, what did they say for that one? 18 data points, so we would look at degrees of freedom 16. So we go to 16, and then follow over 5%, 16, that's 0.468. So your correlation coefficient R would have to be bigger than 0.468 with 18 data points. And then we would consider it a good linear model. All right? If it was less than 0.468, then we consider it a bad linear model. And the reason there's an absolute value on the R is because correlation coefficients can be positive or negative depending on the slope of the line. But you're going to be using Excel to calculate the correlation coefficient. And so it always will calculate it as a positive because it's going to give you an R squared. So you don't have to worry about those absolute values. Just look at R. If it's bigger than this, it's a good linear model. If it's less than that, it's a bad linear model. Closer to 1, the better. The closer to 0, the worse. All right? In a regression problem, R is the correlation coefficient. And tells us how close to linear it is. How close to linear the regression line is. How close to linear the data is. And then it says R squared is called that's called the coefficient of determination. And that tells us the amount of variation in y explained by the variation in x. So variation in y explained by variation in x. All right. So that is page 1 of the review. I'll do another video for page 2 and 3.